Hello everyone, I'm Meghamala, working as Assistant Professor from Electronics and Communication Department, Institute of Aeronautical Engineering. And today I'm going to discuss part 2 of design examples using behavioral modeling. So in the last class, previous class, we have discussed about different types of examples, okay? The design examples in the behavioral modeling, isn't it, based on the registers, based on the operators, and as well based on different operators, and as well using the internal signals, isn't it? Okay, so now in this part 2, we will still more discuss about the design examples using the behavioral modeling. So today mostly we will be pondering on what do we say? We'll be pondering more about on the counters and the finite state machines, Moore and Mealy machines, and so on. Okay, so let's start. Now we will discuss the design examples based on the counters. In the previous classes, we have discussed what is a counter. Okay, a counter is nothing but it is a combinational circuit where it counts the bits from the low to top to bottom, or else from bottom to top, or else from left to right, and as well as from right to left. It just counts the bits. So here in the counters, we have different types of counters: up down counter, ring counter, isn't up down counter, ring counter, okay, and so different examples of counters we have discussed in the later previous classes, and now we will see how this counter is used in order to build a particular circuit diagram, or a particular combinational circuit, particular module. Okay, how these counters help us to build a particular module. Okay, though it is a complex module or else it is a simple module, how this counters will help us to build it. And now we will see the designing part. Okay, so here in the counters, we have, let us see in the behavioral modeling. In the behavioral modeling, how the counters can be written in the form of syntax, or in order to write a program, how we will be writing pertaining to this counters, we will see in detail. And now in the behavioral model, we have module counters. As I said you, module is a keyword. Okay, module is a keyword. Already we have discussed in the previous class about the keywords. So here, whenever you are writing a program, always remember that we need to write or else we need to start the program with the keywords. Okay, so in the syntax, or else in the program, there are different sections. First section is all about initialization section. In the initialization section, we will be starting the syntax, or else we will be starting the program by initializing the inputs and as well as the outputs. Okay, so this is the initialization section. In this initialization section, we will be mentioning about the module that you are considering. So always remember that, always start the program, always start the syntax with the keywords. That keyword should be module. Okay, module, and here name of the module, name of the logic circuit that you are considering. Okay, name of the logic or else the combinational circuit that you are considering. Module, keyword, and then follows with the pertaining to the module. Okay, whatever the circuit that you are considering, that you have to mention here, counter, and then followed with the port list. This is a port list. As we all know, in the port list, always remember the output port should enter first and then follows with the input ports. Okay, output ports first and then input ports and then in-out ports. Okay, this is how we need to mention in the port list. So here, counter, here my inputs are clock and reset. Okay, and the output is register 3:0 Q. So totally, I'm going to count 4 bits of data. Okay, 4 bits of data I'm just going to count. So here, now counter using always block. Already we have discussed always, when the keyword always is used. Okay, and sometimes we will be using always, and sometimes we will be using assign. depends upon the modeling style that you are considering. If I am considering a behavioral modeling style, then my syntax, my main thing, or is the main execution part, these are the main sentences where I am responsible of what am I doing. Okay, so here if I am going for the if I am going with the behavioral modeling, then obviously my keyword should be always at the rate. Okay, if I'm going with the data flow modeling, then my keyword should go with the assign. Okay, data flow. If it is a data flow, assign, or else if it is in behavioral modeling that you want to develop a module or a circuit, then you must represent it with the always at the rate. In the previous class as well, when we are discussing about the registers, okay, in the registers, like we will be using different flip-flops, right? So what is a flip-flop? Flip-flop is a one bit of just one bit of the storage element where it stores only one bit of data. Okay, in that in the example that we have considered flip-flop, in that flip-flop as well, we have considered, or else we have designed the flip-flop with respect to the behavioral modeling. Okay, with respect to the behavioral modeling. So when you are supposed to model or else design a particular module, then pertaining to the modeling style, the keyword should mention. Okay, the initialization of keyword is important. That if you are going as per the behavioral modeling, then you must represent always at the rate, or else if you are going as per the data flow modeling, then you must represent with the keyword assign. So here my counters I'm going to represent in the behavioral modeling. So in this case I must represent the keyword with always at the rate. Okay, always at the rate, passage clock. And now we'll see if and else. If, else, or as well, these are the keywords again. As I said you, this is the initialization of this is the first part where we will see the initialization. Okay, and this is the second part where we will see the actual demonstration, or else actual demonstration of a particular module is been discussed over here. And this part is about the third part. This is about the termination part. Okay, so in the actual part, okay, in the demonstration of the actual part, we must represent the actual part with the statements, or else with the net declaration statements, or else continuous declaration statements, what sort of modeling style that you are considering. Based on that, we must declare here. Okay, so here as I'm considering the behavioral modeling such that I'm using always at the rate positive edge clock. And then if reset, okay, if reset, we are discussing about the counters, right? So if reset q less than or equals to 4 bits 0, as we are discussing the counters, and my counters I'm going to count 4 bits, 3 is to 0, so it is a 4 bits, isn't it? So if reset q less than or equals to 4 bits of data from, that is 0, and then if q less than 0, if not, what happens? My q will becomes q plus 1. Okay, so that means what? From here 0 to 3. So 0, 1, 2, 3. So totally 4 bits, 1, 2, 3 and 4. So 4 bits to for each and every bit should, if I'm using a counter, then I need to increment one bit. Okay, for that purpose I'm writing here q plus 1. Okay, that means what? From q is equals to 0, I should approach 3, isn't it? So 0 to 3, totally 4 bits of data I have to acquire, right? So in that purpose, as I'm using up counter always will represent with plus q plus 1. If it is a down counter, we must count from up to down, isn't it? So for down counter, we'll represent with q minus 1. And for up counter, we'll represent q plus 1. Why? Because we must go up, we must approach to the topmost place, right? From the down, we have to approach the topmost place. That means what? We must increase one bit, and so on. So such cases, like for the up counters, I'm representing q less than or equals to q plus 1. If it is a down counter that you are considering, and then you have to write here q less than or equals to q minus 1. Okay, and then follows with the termination module, termination keyword, that is end module. Okay, if you observe the figure here, this is a counter figure. In this counter figure, we have a clock signal. Okay, and as well we have a reset signal connected to the counter. So for example, as we are saying that this condition is always for the up counter, isn't it? Up counter. So here the example that we have considered is up counter. Okay, so D is a data. How much of data we are counting? 3:0. So 4 bit of data I am counting. So how much of the output that I can acquire? That means it's a 4 bit. I must count from 0, 1, 2, 3, 4. So totally 4 bits of counting I have to do. And then this is nothing but the counters. So Q is equals to 3:0. As it is a up counter, we are representing it with plus. If it is a down counter, we will represent with the decrement sign, negative. So this is about the counters, how to design a module based on the counters, and this is how we will be writing our program or as a syntax in the behavioral modeling. Always remember, in the behavioral modeling, we will be using always at the rate positive edge clock. Okay. So if we are going for any data flow modeling, then always remember S sign. SN is a keyword. Okay. So this is about the counters. And then in the previous is about the behavioral modeling, right? And now we will see about the structural modeling. What is the structural modeling? Structural modeling is nothing but forming or else designing a circuit in the proper structure. Okay, how the structure will be made? The structure will be made with respect to the peripheral devices. For example, if I want to construct some, for example, counters. Or else if I want to construct from some adders, okay, adder, half adder, I'm planning to construct some half adder, design some half adder. How will I design? To design this half adder, I need the registers, right? I need the registers, I need the flip-flops, I need the clock, okay, and as well, I need, what else I need in order to design a half adder? These are the things I need, right? So, first, in the structural behavior, first and the foremost thing to remember is, first, the designing will come from the peripheral devices, the small devices. The designer, being a designer, he should model, okay, he should build up a small components first, and then finally connecting all the components, he can able to connect a structure. Okay, he can able to form a structure, and we are naming that structure as half adder. Why? Because we are planning to module, or else we are plan to construct a half adder. So in the case, I've structured a half adder being accumulating all the peripheral devices, or else all the small devices together. Okay, and now we will see in the counters, based on the structural behavioral, how a syntax or else a program can be made. So here module, the same counter I'm taking. This is same like in the behavioral modeling. Input clock, reset, and output 3:0 and Q. And here the changes will be seen. When you compare behavioral and the structural modeling, the changes can be seen over in the declaration part. So here, wire 3:0 next to Q. Why we are mentioning wire here? Why? Because we are forming a structure, right? So for example, as I've took this example as half adder, first thing I have to do, registers. I must connect the registers. Okay, before connecting, I must connect, or else I must design the flip-flop. First flip-flops, and then registers, and then I'll go for the clocks. For example, okay, so here, to connect these internal devices, okay, to connect these internal modules, what I need the wire, isn't it? In order to connect some gates, these are the gates I've given to OR gate. What is the source? The source is wire. Why? Because in order to form a structure, I'm using all the gates. I need to connect all the gates, and finally I should form it as a structure, isn't it? So, in order to form it as a structure, I need a source called wire. With the help of wire, I can connect all the gates together. So, here, wire 3:0 next to Q. Why I'm mentioning here next? Why? Because as it's a up counter. Okay, my counter is up counter. So, I must go from down to bottom to top, isn't it? So from 0 to 1, I must increment 1. From 1 to 2, I must increment 1 again. And from 2 to 3, I must increment 1. And again from 3 to 4, I must increment 1. So in the case, have to go for next, next, next. So here, wire is meant to connect the peripheral devices or the internal modules, and then next queue. So counter using module calls. Okay, here the counter is using the module calls. Module calls is nothing but the next queue. So flip-flop queue. So for this, I'm considering the flip-flop. Why? Because just to store the bits. Okay, as we need to count from 0 to 4, I must store the bit and then I must release a bit. Then only I can go from bottom to top, isn't it? So for storing purpose, I'm using the flip-flop. So here, flip-flop. So for this flip-flop, I have clock, reset, and next, and then queue. Okay, what is the purpose of next queue and queue? Next queue is nothing but the, I'm just going to increase one bit, right? So next bit 1 and next bit 1. And then queue is nothing but the bit which I have stored. For initially I have stored 1 bit, and for next bit plus 1 I have added. So queue plus 1. So adder, increment, as it is a up counter, I must increase. Increment, queue 4 bit 1, next queue of next of queue. So here, as it is a up counter, I must increase one bit such that queue is a register that it will store. How many bits I am going to count? 4 bits of data with the increment of 1. Next queue is nothing but the plus 1. Okay, increment of 1. Next one. And here assumes 4-bit adder end module. So here I have considered half adder, right? So in the half adder, what I've considered all the registers, flip flops, and the clock as well. In the if you are considering a 4-bit adder, so if you are considering a 4-bit adder, I have to consider the registers as well. I must consider the flip flops as well, and I must consider the clock as well. Okay, this is a 4-bit register, 4-bit adder. That means what? I must add the 4 bits, 0, 1, 1, 1, 1, 0, 1, 0. So here I have to add 4 bits, and here also as well I have to add the 4 bits. Okay, this is about the 4 bits, and then finally we are terminating the syntax with the end module. Okay, this is about the counters, the designing of the counters in the structural behavioral, in the structural model. And coming up with the combination logic with always block. So here in the behavioral modeling, we have discussed always at the rate is a keyword where we have to use when you are considering or else when you are modeling a particular circuit in a behavioral modeling, right? So here always blocks are often sequential. So here always at the rate, isn't it? Always at the rate is a keyword where here it states that the execution of the program can take place in a sequential manner. Okay, one after the other, sequential manner the execution can take place. So, but if you have all RHS variables in the sensitivity list, it can be combinational. So here, as I said you, in the sequential always at the rate, the block always are often sequential, but also they can be a combinational as well. Okay, and remember that you still must assign to a register. So though you are using a always at the rate in the combinational and as well as in the sequential, always remember that you have to assign the values, or else you have to give the assignment to your proper registers. So this is an example we will see here, module inverter. So this is nothing but a simple inverter we are considering. So for this inverter, what is an inverter? If your output is 0, if the input is 0, output you will obtain as 1. And if your input is 1, and you will get the output as 0. Quite opposite, isn't it? So in order to explain the example in the combinational logic with always block, here we are considering a simple gate called the NOT gate or as inverter. Module is a keyword, inverter is a module that I am considering, and in the port list I am representing input and as well as the output port. So my input ports are 3:0. So again 4 bits of data I am considering, and output register is 3:0. That means what? If it's 0, 1, 0, 1 or 0, 1, 1, 1, my output goes like this, 1, 0, 0, 0. Okay, here you can consider 2 is to 0. Any number of bits you are flexible, you can consider. But remember here, always at the rate star. Okay, so always at the rate star. Why? Because A complement, A is equals to A complement, and we represent A is equals to A bar. Okay, A is equals to not of A. So this is how we will represent, right? So always at the rate star, and that is Y is output. Y is less than or equals to negation of A. Okay, as it is a NOT gate, we are representing that when input is 0, we will get the output as 1. So here Y is less than or equals to negation of A. And the N module. Okay, finally we are terminating it with the N module. So this is how we will write the combinational logic with always block. Always remember that always blocks, always at the rate block can be used not only to the combinational, or it's not only to the sequential, but also we can mention when it can be a combinational as well. And then coming up with the decoder example. So here we all know what is a decoder. Okay, decoder is nothing but which decodes a bits. 3:8 decoder, isn't it? N into 2 power n. This is what the decoder says. If n bits, input, 2 power n bits is the output. 3:8 decoder. And then 4:16 decoder, isn't it? Okay, 64 decoder. So here we will see as decoder is a combinational circuit, and now we will see how syntax can be, or how a program can be written with the help of always at the rate. That means in the behavioral modeling. In the behavioral modeling, you will see how a program can be written when it comes to the decoder, when you're considering the decoder. So here, 3:8 decoder they have considered. 3 input, 8 output. So 3:8 decoder. That means what? N into 2 power n. 3 into 2 power 3. So 3:8 decoder. So here we will see module, and the example or else a module that I am considering is a decoder. Always, okay, decoder always, and the port list consists of input 2 is to 0. That is totally 3 bits of input, and output is, as it is a 3:8 decoder, 3 is the input and 8 is the output. So when I am representing 3 bits, I must represent 2 is to 0 as input and 7 is to 0 as the output. So here my output is register 7 is to 0. Why? So it is a 3:8 decoder. Okay, and now we will see always at the rate star case here. So we are and as well we have discussed a few what do we say? Few lexical tokens, isn't it? Few lexical tokens based on the modeling styles that you are considering. So here case, end case, case, end case. And as well as we have discussed about the front, begin, okay, fork, begin and fork, case, end case. So these are few lexical tokens that we have discussed, and these lexical tokens will help us to write the program based on the combinational or as a sequential circuit that you are considering. Okay, when you are considering a decoder, remember that you can write a program based on lexical token of case, end case. So why we are going for the case? Why? Because here we have the input 3 and the output is 8. 8 combinations, isn't it? 8 combinations of output we are obtaining. So here my bits goes from, as it is a 3:8 decoder. So my output from 0 to, it is 1, 2, 3, 4, 5, 6, 7, 8. So here 3 bits of data from 0 to 7. We all know the binary bits, right? Binary 0 represented with 0, 0, 0. Binary 1, 0, 0, 1, 2, 3, 4, 5, 6, 7. Isn't it? And then you will see the 1. Okay. The 1, it goes from, when you are going from 0 to 7, what happens? The enabling bits will, it just take its position towards the left. So it is 0 finally, and for 1, it goes to the leftmost position, and then like that. For finally, you will obtain the positioning of 1 at the first bit. Okay, MSB bit, and then finally end case, and then the end module. So this is about a figure states that it's a 3:8 decoder, right? So here 1, 2, 3, 4, 5, 6, 7, 8. So this is the 8 output, and here we are giving the 3 inputs. 3 inputs, 1 at a time. 3, 1, 2, 3 for first D1, D2, D4, D5, D6, D7, D8. Isn't it? For 0th bit, D1 is enabling and all will disable. D2, D3, D4 like this. D1, D2, D4, D5 and so on, D7. Okay, so it will enable this will enable 1, and for the next the D2 will enable and all will disable, and for third case D3 will enable and the rest of the things will disable. And likewise for the fourth case, that is when all the inputs 1, 1, 1, what happens? My D8 will enable. Okay, that means what? It becomes 1 and all my D8 will becomes 1 and all my D7, D6, D5, D4, D3, D2, D1, D0 and all will becomes disable. Okay, so this is how we can write the example using a behavioral modeling with respect to the case and end case. Okay, it is very simple to remember and as well to analyze. And then we'll go with the another example. It is 7-segment decoder. Okay, this 7-segment decoder is nothing but, for example, you might have seen in the bus, the transport kind of things. When you want to go for one place to another place, in the present days, we see that there are the digital displays, isn't it? Digital displays not only on the transportation, but also in the different various shops also we can find. Okay, for example, if you went to buy something in the shop, you can see the weighing machines are in the digital forms, right? You will see the numbers in the digital format, and the weighing balance, for example. So there you will see the weight. That weight will be, it's nothing but it's a 7-segment decoder. That means what? We can see we can see the numbers displayed. Okay, so here this is nothing but a 7-segment decoder. In the 7-segment decoder, we will see how the program can be written and how the execution or else the output can be obtained. So here my module is a 7-segment display, and this 7-segment display, I'm having input data is today 0, that is 4 bits of data, and the output register is 6:7 segment. Why? Because it is 7 segment, right? So 7-segment data means totally 6:0, that is 7 segment. So here 3:0. 3:0 means it's a 4 bit of data. So we will see here the segment A, B, C, D, E, F, G. It is a 7 segment, right? So it is a 1, 2, 3, 4, 5, 6, 7. So if you want, okay, for example, parameter blank. That means what? In the display, if you want to see the blank, nothing should be nothing should be there on the display part. So if you just want to see the blank, what happens? All my bits, 7 bits of 0, 0, 0. That means what? A should become 0, B should become 0, 3, 4 as well, 5 as well, 6 and 7 as well. If all are disabled, okay, if all are disabled, then I can see the blank one. And if I want to see the 0, okay, if I want to see the 0, what I should do? In order to see the 0, B 1 1 1 1 1 1. That means what here? If I want to see 0, how the 0 I can see? See, it should become A should become 1, B should become 1, and C should become 1, D should enable, E should enable, and F should enable. And my G should become 0. Okay, G should become 0. G should become 0. If it is 0, what happens? The rest of all A, B, C, D, E, F are 1, right? They are enabled. So what can I see? Now I can see all the segments A, B, C, D, E, F. All these segments are in the on state condition, right? When they are on, I can see a clear 0. Likewise, if you want to see the 2, okay, number 2. So in order to see number 2, what should I do? Which segment should I should get enable? 2 means 1, 2, 3, 4, 5. That means what? A should become 1, B should 1, G should become 1, and E should become 1, D should become 1. So all these segments should become 1. F, F and C, except F and C, the rest all should become 1, such that I can see only 2. For example, if I want to F and C should become 0. And for example, if I want to see number 9, okay, if I want to go for the 8 means A is equals to 1, B is equals to 1, G is equals to 1, F is equals to 1, C is equals to 1, C1, D1 and E1. So here I can see my 8. If I want to see only 9, if I want to see 9, this is my 9, right? So here E should disable, E is equals to 0. Except E is equals to 0, the rest of all are in the on state condition, then 9 will enable. Okay, 9 can be displayed. So this is how the displaying part, this is how the enabling and disabling of the things goes on as per the numbers from 0 to 7. And here always at the rate case. Again we have come with we are considering the case and the end case. So here if it is a case 0, for case 0, segment less than or equals to 0. If it is a case 1, segment less than or equals to 1. And for different segment, for segment 9, what it says in the case segment less than or equals to 9, by default, segments less than or equals to blank. Why? Because we have considered blank as well. Okay, from 0 to 7, right? From 0 is nothing but the blank. So by default, what happens? All the segments from A to E, or all the segments from A to G, they become 0. So by default, if they are 0, then we are saying it is a blank. So default segment less than or equals to blank, and then we are terminating it with the end case, and then finally with the end module. So this is an example. It's a very good example for the exam point of view. If you are getting any question based on the behavioral modeling, consider a combination of circuits based on the behavioral modeling. Means simply you can study this, analyze, and then you can write the answer. Okay. So here this is a 7-segment decoder where we are displaying all these 7 segments, all from 0 to 7. How the displaying part can be seen from 0 to 7 with respect to 0, 1, 2, 3 until 7. How display can be seen using the behavioral modeling kind of style. Okay, and then we'll go with the memories. So here memories, we have different types of memories, right? Primary memory, secondary memory, and so on. Okay, and as well in the previous years, you might have studied in the computer organization subject. You might have studied different types of memories. What are the different types of memories? We all know as RAM, ROM, and under the RAM and ROM, we have the different types of categories: EROM, EPROM, PROM, EEPROM, isn't it? So here the generalist translates to block RAMs onto a Spartan 3 FPGA. Okay, this Spartan 3 FPGA is nothing but it is a software where you have to, like, it's a backend. For the backend process, mostly we'll be using the Spartan 3 software, FPGA, field programmable gate arrays. So here, in order to translate to block the RAMs, usually we'll be using this. So here we will see in terms of memories also, how can a program can be made, or else how can a program can be developed. Okay, so here module, RAM, the memory. My inputs are input clock, input adder, 6-bit of adder, and input wire, and then my input are 16 bits of data input I'm considering, and to the output 16-bit of data output I'm considering. Okay, so here this is a memory. Totally how much of memory that we are allocating? 16-bit of memory. Okay, so this is a RAM one, 16-bit of memory. So this is a 16-bit of memory representation D out, and here for this memory I have address bits, I have data bits. Okay, for read and write purpose I have for enabling and the clock. Okay, so this is the address bits, for data bits, and the address register, data register, and here the total of 6 bits of data register, address register, and this is a enable, and this is a clock. Okay, so here we will see register 16 bit of data. So 16 bit of data I am going to store in the register. So how much of memory? 16 bits of memory is 64 bytes of memory, isn't it? So 64, that is a memory is of totally 64 bytes, whereas the address bits are totally 16. See here, 16 data bits, the data bits of 16 data bits. Okay, and here using the always at the rate positive edge clock. Okay, we have a clock signal, so always remember, rather than going for the negative edge, better we go for the positive edge. So always at the rate positive edge of the clock. Here, if my bit, okay, if my read and write enabling bit, this is read and write enabling bit. If my read and write enabling bit is not enabled, what happens? The address in the memory will become then less than or equals to input. Okay, so this is a statement, so you need to ponder more on this. That is, if I'm not going to read and write anything from the memory, what happens? Again, I go back to the initial state, that is the D input, isn't it? The memory address of D input when negation of read and write of the bits happens. Then finally assign D out. So for this D out, what are we assigning? Whatever the memory that you are allocating with respect to the address bits, data bits, and as well as the read operation for the write operation, and respective with the clock and enabling, whatever the output that you are obtaining, we will be storing in the memory in the address with respect to the address bits, right? So if it is 64 bits of data we are storing, and then it should be stored in the memory, that is of memory of 64 bits of address bits. So assign D out, which is equals to 64 bits. So this is how even for a memory allocation the program can be written. Okay, and then blocking versus non-blocking. So regarding this blocking and non-blocking, in the previous class we have discussed what are the blocking statements, what are the non-blocking statements. Under blocking statements, what sort of keywords that we have mentioned, and for non-blocking statements, what sort of keywords we have mentioned. Okay, the keywords and as well the initialization of the inputs and outputs, it could be in the vector or else in the scalar form. Any kind of form can be stored. So here under the shift registers, what is shift registers? Shift registers are nothing but they shift the bits either from left to right, or else from the right to left. Okay, shift left. When the bits are shifting from right to left, we call it as a shift left. When the bits are shifting from left to right, we call it as a left shift. So here we see the module shift register, inputs are clock, okay, and one more input is in S, and then output of 4 bits I am going to shift. How? Using the either the shift left operation or also shift right operation. So this is the correct implementation using non-blocking statement. So when you are here, we are writing a program based on 2 conditions. One is blocking and as well as the non-blocking. So here using non-blocking assignment, how can a declaration part can be written? So always at the rate positive edge clock begin. So as it is a 4 bit of data, Q is equals to 0 to 3, isn't it? So for Q is equals to 0, less than or equals to S, that is 1 bit, that is blocking statement. Non-blocking, okay, for non-blocking we represent less than or equals to, okay, we know what is equals to, it is an assignment operator, isn't it? So for non-blocking we represent less than or equals to, and for Q is equals to 1, less than or equals to Q is equals to 0, for 2 it is 1, for 3 is 2. Okay, so 0, 1, 2, 3, we are representing as 0, 1, 2, 3. That means what we are shifting towards the left. If it is a 0, 1, 1, 1, 0. So if it is a left shift, we will be shifting towards the left. So here it will become 1, 0, 1, 1. And then for the next case, we are shifting one more time. So it will become 1, 1, 0, 1. And for the third case, we are again shifting, isn't it, to the left. So it will become 1, 1, 1, 0. Isn't it? So here the bits, first bit will always is 1, S, and 0, 1, 2, 3. So this is how the representation takes place. And then even better to write. Okay, if you just want to write, then how can we how with the conditional statements or else with the continuous procedural statements, how the statements can be written. So if you want to write in a better way to write, Q less than or equals to totally 3 bits of data you are shifting, right? You have to leave this one. Why? Because it is going to shift towards the left side or else to the right side. So we have to leave this pointer on 3 bits. So here 2:0 S in. Okay. See here the flower braces. What are these flower braces? Flower braces is nothing but the concatenation. So what is mean by concatenation? Concatenation is clubbing of two things, right? So here I'm concatenating both Q and as well as the shifted bit as well. So this is a concatenation of both is being done, and then finally terminating it with the end. Why? Because here I've begin with the keyword begin. So I must end with the keyword end, and then finally the whole program can be ended with the end module. So this is how we can write pertaining to the non-blocking shift registers. So for the non-blocking, always remember this is how we need to represent the equations to the on towards the LHS and on towards the RHS. In order to separate these two, this is the operator that where we have to represent. Okay, this is about the shift registers for the non-blocking statements. And here, so this is a shift registers for the blocking statement. So when you observe this non-blocking and blocking statements, the declination part is same, the initialization part is same module shift register. As it is a bad implementation, that means what here, there's a difference that you have to remember for blocking and non-blocking is always at the rate positive edge clock. So here also always at the rate positive edge clock when it comes to the non-blocking. But here you will see for blocking statements, we are representing only with equals to. For the non-blocking statements, we are representing with less than or equals. This is for blocking statement. So here simply, okay, without any complications, simply we are representing. So Q is equals to 0, S in Q1, 2, 3. So 0, 1, 2, 3 and an end module. So here the better thing that we have written is in order to write all the bits together, or else if you want to concatenate all the shifted bits and as well with the shifting bits and as well with the accumulated bits, this is a better way to represent Q less than or equals to concatenation of both the bits. That is Q is equals to 3 bits and as well as a shifted bit S in. Whereas here in the blocking statements, we are nowhere representing any kind of things if you want to shift all together. Okay, so this is the main difference between the blocking and as well as the non-blocking. We are not representing anything, any kind of shifting bits accumulated. Okay, so simply we are just writing how the bits are shifted and then we are terminating simply. So, and also the thing we have to remember is the blocking statements always mentioned with the operator, assignment operator, that is equals to. For non-blocking statement, less than or equals to. Okay, this is about the shift registers between the difference between the blocking and the non-blocking. And coming to the finite state machines, this finite state machines you will be learning more in the last module, that is 5th module. In this finite state machines, we will be pondering more about the different types of the things like machines, different melee machine, more machine, and so on. Okay, and different types of the state. The transition occurs between the different states. Okay, the transition, how the transition is occurring between the different states. So here it divides into 3 sections. So this finite state machines, it divides into 3 sections: state register, next state logic, and the output logic. So this is the things you will find in the finite state machines. You will observe the finite state machines. So use parameters for state encodings. So for each and every state we have to represent the parameters S1, S2, S3, and we must represent with this state transition 0, 0, 0, 1, 1, 0, and 1, 1, and as well for the next transition it should represent with 1, and if it is representing here itself in itself, we will represent it with a 0. If it is passing on to the next transition, obviously we will mention with the 1. So here we use parameters of the state encoders in the finite state machines, and as well here in the FSM finite state machines we will see the 3 states: no inputs, no outputs, and 2 state bits. So we will regarding this finite state machines we will deep learn in the coming modules. Okay, so as per this, as of we are learning about more about the designing of the combinational circuit. So how a model can be designed using finite state machines. This is how that we can see. So here there's 3 state, no inputs, 2 outputs, and 2. This is just a small example how to represent the state transitions between, see here we have three state S0, S1 and S2, and see this is divide by 3 counter state transition. So this figure is about the design divide by 3 counter state transition. So here you can see for S0 state, you see the out is equals to output is equals to 1. Then if it is 0, it's moving on to the next transition. The transition is taking place to the S1, and we have the output as 0. And after S1, the transition is taking place toward S2. So the output we are observing as 1. So here you will see the output when the transition takes place between the different states. You will see the output is being changes. Okay, from 0 to 1 and 1 to 0. Okay, and this is a simple example. This is also based on the behavioral modeling. Okay, this is a simple example pertaining to the finite state machine, and this program is all about with respect to the behavioral modeling. So here we will see module divide by 3, FSM, finite state machine divide by 3 counter, as we have seen in the previous slide. So here we have input clock and input reset, and as well as the output. So we will be representing the inputs with clock, reset, and as well as with the output out. So the registers 1:0. So how much of data we are considering? Only 2 bits of data. It should be 0 or 1. 2 bits of data. So state, the next state. If it is in that state, we will represent the bit will be in that particular state when it is 0. And if the transition is taking place, it will go to the next state. Okay, and then the parameters S0, S1, S2. Okay, these are the 3 states we are representing with the parameters S0, S1, S2. And if it is 0, 0, it states with the state transition is with respect to that particular state S0. If it is 0, 1, it goes to S1. If it is 1, 0, it goes to S2. Okay, and then now we will see, this is all about the declaration, initialization state. So in this initialization part, we will be initializing all the inputs and as well as the output with respect to the combination circuit that you are considering. And coming to the declaration part, which is the most important second part, here we will see the state registers. So here the state registers, as we are discussing, as we are using the behavioral kind of modeling, we are always at the rate is a keyword, always at the rate, positive edge clock and positive edge reset. Okay, so the clock and reset, the positive edge that you are considering that, and it should be initialized at the always at the rate. And then here the condition follows like this. If reset state less than or equals to 0, if not, what happens? It goes to the next state. If as per my input, if the transition is within itself, then my state will be in that particular state S0. If not, the other condition is it can goes on, or the transition takes place to next state S1. And when it comes to the next state, this state will become the first state. So as per the output, if I'm getting, if my transition is within if my output is within that state, then my first state will become S1, and then if not, my transition goes to the next state S2. Okay, likewise, the transition between the different states takes place. So if reset less than or equals to S0, if not, it goes to the next state. And then here the state logic follows like this. The state logic is always at the rate star, and then here I'm considering the case and end case. So here if you see case state, why? Because here we have different state S0, S1 and S2. Okay, these are the state S0, S1 and S2. Case state S0, which is equals to next state. That means what? If the transition takes place from 0 to 1, then the state will change from S0 to S1. And then the next, as I explained you here, the same we are representing over here. S0 to S1, S1 to S2, and S2 to S0 again. S2 to S0 again. Why? Because here we are considering only 3 states, S0, S1 and S2. The transition occurs between these 3 states. So finally, by default, the next state would be obviously S0 itself. It will not go to, or it will not extend towards the other states. Why? Because here we have the parameters or the states that we have considered only the 3 states, that is 0 to S0 to S1, S2. So finally, by default, it goes again back to S0. And then I'm ending up with the end case and end module. Okay, so this is all about the finite state machines. Now, in the exam point of view, if you want to write any examples, if you want to give any examples, this is the best example that you can give, so that you will score good marks. So this is about the Mealy and Moore. We will in depth discuss about this kind of thing in the module 5. So this is just for a glance I have given. So this is about Mealy, this Mealy and this is a Moore. So in the Mealy and Moore, you will have the next logic state and output state, followed with the next state and clock. So you have to tell me the difference between these two. Okay, so here if you see the difference, we will see the logic, the output logic. We see the inputs. The input is given to the next state logic, and then it goes to the logic output, and then finally with the logic state, right? So here you can see the feedback is again, the feedback connection is again given back to the next state logic. Whereas whereas here in the Moore mission, you will see we have a feedback path, but when it comes to we have feedback path. That means for here you can I can give you a best example when it comes to the flip-flops. In the master-slave flip-flop as well, we have this, right? Master, slave. So what happens here? So this kind of transition will take place between the different states, that is set master and as well as a slave. Always when it comes to the flip-flops, always master state, it will initiate the signal first. Okay, it just initiate the signal first. So this is just for a glance of view. I have given the this slide. This is not that much important when it comes to the design of examples as we are discussing now. But when it, for the exam point of view, always remember that go for this finite state machine. You can give a finite state machine example, and as well as you can give the decoder example. Okay, and as well as you can give the multiplexer example. Okay, in order to write any program, always better to give the examples of based on this FSM, decoders and multiplexers. That would be more enough. I hope you all understood this class, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.